Good morning, folks. So we are approaching our last assessment, or at least one of our last assessments of the year. I'm gonna on Monday give you guys a short project, and I'm gonna give you 3 or 4 days to work through it. It's really not that major of a project, but it is a nice application. It's something to kind of connect uh, this topic of volume to the real life. But before we get there, I wanted to introduce an example or a special case of solids of revolutions that may come into play with the project. Depending on how you guys want to navigate the project, some of you might have to deal with something like this. So let's give another example. It's nothing too crazy, I promise. Um, we are going to have a region given to us bounded by the equations we see here. And I want to find the volume of that region rotated around the x-axis, right? So the three equations are square root of x, negative x plus 6, and y equals 0. Basically, y equals 0 is the x-axis, but I'm giving it a more formal name. So of course, the first thing you always want to do is graph the region. And we see, of course, our purple curve, square root of x. We see our pinkish, maroonish line, y equals negative x plus 6. And then we see the x-axis, which is the y equals 0. So this region right here is the one that's bounded by all three. Obviously, there's three other regions, but this is the only one that touches all three and is completely enclosed. That's what it is. That's what it means to be bounded. So I also wanted to point out a few things. With a region of this type, you always want to get your points of intersection kind of emphasized as well. So we have, of course, the origin 0, 0. We have the x-intercept of our line, 6, 0. And then, of course, I can set the two equations that hit here, square root of x and negative x plus 6, set those equal to each other and solve for x, plug it in, get the y coordinate. That's 4, 2. So why is this a unique case? Why is this different than the ones that we've seen before? Well, in order to do that, I'm going to first kind of blow up the image here of the region that we just contained. And I want to show two things. So I'm emphasizing a cross section a little bit further on the left side and then a different cross section a little bit on the right side. So again, the base of this region, this is the y equals 0. This is the x-axis. On the left cross section, the upper part of this would stop when it hits the curve square root of x. Okay, so here the radius is square root of x. Over here, though, the upper part would hit the curve negative x plus 6, which means that radius is different, negative x plus 6. And in fact, everywhere to the left of this intersection point at 4, 2, everywhere to the left, the radius is the square root of x. Everywhere to the right, the radius is negative x plus 6. So it changes the function for the volume depending on where in this region you're located. Okay? So that's a problem because I can't change a function in the middle of an integral. What I can do is split this volume up into two integrals. So the first integral we have here, notice I'm not going the full region. I'm going 0 to 4 because the square root of x acts as a radius starting at the x coordinate of 0, and it stops acting as the radius when we get to the x coordinate of 4. And then I'm going to kind of pivot, and I'm going to change my radius to the negative x plus 6. And that starts acting as the radius in this at 4, and it stops at the other endpoint of an x coordinate of 6. So 4 to 6, the radius is negative x plus 6. Now, of course, it makes sense if I add up this region, it's almost like I'm cutting the region into two. If I rotate this little triangular region 360 degrees around the x-axis, I get the volume generated with this integral. And if I take this square root region, rotate that around the x-axis 360 degrees, I get the volume generated by this one. Adding them up, I get the full region's volume. So here, it's not terribly difficult, but if that radius function ever changes or is not consistent from one end of the region to the other, you have to figure out where does it change, and it's going to be at the point of intersection, and then split into two integrals, one for either side of that point. Now, once you set up the two integrals, from there, it's just basic integration, right? So square root of x squared and then negative x plus 6 squared. I simplified both of those integrals, and then I just integrated, and I substituted in, and I got my final answer, 33.5-ish units cubed. So this is actually very common in real life applications because it's difficult to go with a basic function from one end all the way to the other. A lot of shapes require multiple functions. So it's not uncommon to see this in practice. So I'm going to leave it here. I'm not actually going to assign anything for the weekend. You guys just took a nice quiz. I'm going to give you the weekend off. The project next week is going to be dealing with you are creating going to be creating an integral to create a three-dimensional object. I'm not actually saying you have to create a three-dimensional object, but you're basically going to find a picture of some object that I can then rotate around and create a three-dimensional object. I'll put way more information about the project in on Monday's course post, but I want you to start thinking of common objects, something you might have around in the house that would look like I took a two-dimensional picture and it was rotated 360 degrees. My example would be like a football. A baseball bat's huge, but a baseball bat is something that was rotated 360 degrees. I just chugged a glass of my water because I saw this out of the corner of my eye. My cup. This cup is a nice rotated volume of revolution. Now, of course, I would only want half of it because it's the region that's rotated. And you can see it even has some nice like curves here. Now, we'll get into more details on Monday, but that's kind of what the project's going to be dealing with is finding an object and then using that object to create some equation, some region, and of course the integral for the volume. So start thinking, get creative, and look out for the project on Monday. Enjoy your weekend, folks.